Welcome to the Crazy Hat Chemist. So another video here on chemistry and kinetics. Bam! So today we're talking about a kinetics mechanism example number 1. Okay, nitric oxide, aka nitrogen monoxide, is reduced by hydrogen to yield water and nitrogen gas according to the following balanced equation. So there it is right there. You see 2NO gas plus 2H2 gas produces 2 waters, gaseous state, and nitrogen, which is of course one of these, and that is a diatomic molecule. Okay, and that's in the gaseous state. All right, a possible mechanism is below. What is the rate and molecularity of each step? Is there a catalyst, yes or no? If so, what is it? And are there intermediates? And if so, what is or are they? So here is the possible mechanism. Notice when I wrote out this mechanism, we're keeping all our ducks in a row, and that is all the arrows are in a row. Okay, this is a sequence of 3 molecular events. The first one there you should see is an arrow that goes back and forth. That's an equilibrium type of reaction, and we're going to be discussing those a little bit later on here. Okay, the second one has a unidirectional arrow. The third one has a unidirectional arrow. So what you're going to do is analyze this reaction here. Really take a look at each molecular event. Since each molecular event is a molecular event, you can actually determine the rate law based on the stoichiometry and the reactants. So remember, rate laws are based on reactants only. So we're going to write rate laws. Okay, so the first molecular event is R is equal to K NO squared. Notice that that squared term is there because there's a 2 in front of the NO. And I am not including the N2O2 because that is a product. Remember, rate laws are only based on reactants only. And what is the molecularity of this event? It is bimolecular because that superscript there, that exponent is a 2, so that's bimolecular. Okay, let's determine the rate law for the second elementary step. And again, because it's an elementary step, we can write the rate law based solely on the stoichiometry of the reaction itself. And knowing that it's an elementary step, that works perfectly fine. Remember, rate laws are only based on reactants only. So here is our rate law. R is equal to K, that's our constant, times N2O2 to the first power, and that's because the stoichiometry of the N2O2 is a 1, times H2 to the first power. And again, the first power here for the H2 is because the H2 on the reactant side is a stoichiometric coefficient of a 1. So what is the molecularity of this reaction here on this elementary step? It is bimolecular. So you're adding up the 1 plus the 1 to get the bimolecular. Okay? All right, the next elementary step here, we're going to write the rate law for the next elementary step. Again, the rate law is based on reactants only and using the stoichiometry because this is an elementary step. Okay, and here's the rate law here for this one, for that third one. That's R is equal to K N2O to the first power because the stoichiometric coefficient on the N2O is to the first power, or a stoichiometric coefficient of a 1. And the H2 is to the first power because the stoichiometry on the H2 is a 1. So what is the molecularity of this elementary step? And that is bimolecular. Okay, so we've got the rate law for each elementary step. That's based on the stoichiometry and the reactants only. And we got the molecularity of each one of those steps. Now, is there a catalyst? So a catalyst is something that is not consumed in the reaction. So you see it and then you get it back again, right? You have it a little bit and then you still get it back later on. It's not canceled out anywhere. Okay, and the answer is no. There is no catalyst in this reaction. We're going to do another problem and I'll show you where a catalyst is and how to identify it. Okay, so are there any intermediates? There are most certainly some intermediates. Now remember, intermediates are produced and later consumed, and they are not in the net equation, and they are canceled out. So let's circle some of these intermediates. Here is one of the intermediates. That's N2O2. So you should see on the first molecular elementary step molecular event, The first elementary step, it is produced. The second elementary step, it is used up. So one is on the product side, one is on the reacting side, they cancel out. Can you find any more intermediates? I think you can. You can find one more intermediate, and here is that. Okay, in that second elementary step, it is N2O is produced, and in the third molecular event, elementary step, N2O is later consumed. So you can cancel these out, because when I write the net equation for this, you don't see any of the intermediates. Okay, so the intermediates are N2O2 and N2O. Okay, so I'm going to draw a line right here, and I'm going to add up everything. Okay, if you have something on the reacting side, something on the product side, like an intermediate, they cancel each other out and they are not involved. So this is my net equation. Now, does my net equation from these molecular events correspond to the overall equation at the top? Most certainly it does. And so that is a good mechanism. So a good mechanism is when all the elementary steps sum up to the net equation. It has to be that way. The beautiful thing about a mechanism is if you write a mechanism, then you have probably unimolecular, bimolecular, or termomolecular events, and you can write the rate laws based on the molecularity, that is the stoichiometric coefficients of the reactants only. Okay? And each of the elementary steps will add up. Make sure you pay attention to what the intermediates are, and we're going to pay attention to the catalyst in the next problem here. Okay? Hopefully you enjoyed that video. And I got another crazy hat for you. Got to figure out, is that an alligator or a crocodile? Okay, give me a thumbs up if you like that video. Subscribe to my YouTube channel, and I'm going to see you next time for one more kinetics problem, and then we're done with this unit. All right, I'll see you next time. Bye for now.